Hello, everybody. How are you? Louder. We give you coffee. We give you coffee so that you're excited and enthusiastic about technology, right? About being inside on this beautiful Seattle day. So how was your second day of build? Who is at build for the first time this year? So quite a few. That's awesome. This is also my first build. And it's amazing how huge and how kind of multi-purpose it happens to be. So talking not just about Azure, not just about Windows technologies, not just about kind of the historic and also like brand spanking new Microsoft cultures. It's exciting to be here, and I'm glad to talk to y'all about TensorFlow and Keras. So who here is a machine learning practitioner? Like you do that for your day job? What about data scientists or thereabouts? Okay. Who here saw some salary postings for data science or machine learning and got real enthusiastic? Okay. So excellent. That means that the content is spot on. The kind of general plan for this is that I'm going to give an overview of machine learning and deep learning and talk about kind of the nuances between the two when you would want to use one versus the other. And then also point at a lot of tooling on Azure that's able to support deep learning workflows specifically for TensorFlow and Keras. And then point you at a repo with a whole bunch of sample code, because that's all any of us ever want to see is documentation and sample code. Like if it doesn't have code, it doesn't exist. Cool. So I am, if this works, maybe not. Let's try this. Excellent. I am Paige Bailey. I do things with computers more or less effectively. Have been working at Microsoft since July of last year. I'm a cloud developer advocate focused in machine learning and AI. I have about 10 years of experience with Python, a little bit more, and about 5 with predictive modeling in R. So both languages that are beloved by the data science world, that are beloved by me too. I also have a bit of experience working with Apache Spark, and then also working in kind of a Hadoop ecosystem. My previous job was working for Chevron in Houston, and we used Cloudera as kind of our Hadoop facilitation. And I'm also dynamic web page pretty much everywhere on the internet. So if you would like to go and hang out and talk to me there, we're all good. So roadmap for today's workshop. We're going to talk about some theory. So what's deep learning, what's machine learning, why should you care, and then also how TensorFlow and Keras kind of work into that ecosystem. We'll also be kind of building a neural network from scratch if we get far enough. So talking about how you would go about implementing some of the structures that we see in TensorFlow in NumPy, which is one of the numerical Python libraries. And then also we'll be doing some work with Keras. So understanding why TensorFlow developers even say don't code things just using TensorFlow, use a developer-facing API, because it's a pain in the butt to do. So introduction to deep learning. What is artificial intelligence? And the textbook definition is any technique that enables computers to mimic human behavior. And if you go by that definition, artificial intelligence has been around for a long, long time, right? Like ever since you would have a Turing machine where you can have a specified script and you give the computer an input and it gives you back an output and kind of emulating a conversation, that could technically, by this definition, be classified as artificial intelligence. And the constituent parts of neural networks, they've been around for a long time too. So since the 50s and the 60s as well. Machine learning, though, is a little bit different. And that's the ability to learn without being explicitly programmed. So as developers, and I probably should have asked this question too, how many of you guys are C# folks? Lots. OK, cool. How many of you people are Python or R people? OK, so we've got some there. And then other languages, so like JavaScript or like more web-facing. OK, so healthy mix. That's beautiful. So machine learning is the ability to learn without being explicitly programmed, as I mentioned before. But with traditional programming paradigms, you were tasked with defining all the rules that your inputs should go through to get the outputs that you expect, if that makes sense, right? So you, as a developer, are in charge of defining if-else statements. You have to explicitly program and kind of teach the computer everything that that computer would need to know in order to make a decision. For machine learning, it's very different. You give the computer data, you give it the expected outputs based on that data, and it gives you back the rules. So instead of you having to understand, okay, well, here's what needs to happen in order for me to recognize this dog in this image, your algorithm comes up with that information for you. And what does that look like, right? So this is, again, very, very, very simplified tree. And there's an additional branch up at the top called semi-supervised learning, but we're not talking about that today. But so supervised learning can either be a classification task or a regression task. And if you're doing classification, that's basically recognizing a category, right? So you're recognizing Republican versus Democrat, cat versus dog, red versus blue, true versus false, something like that. A regression task is you're trying to predict a numerical value, right? Like, so I'm trying to, so I will sell 6 widgets in July of next year, or it will be 75 degrees next Tuesday, or something of that nature. So the key thing that I want you to remember about supervised tasks is that they all require for you to know what the answer would be, right? Like you have to classify specified images. You have to classify the result of a particular value. Unsupervised learning is much less straightforward. And there was actually a tweet a couple of months ago saying that instead of trying to do an unsupervised learning task because it's very, very difficult, you don't know the answers, what you should do is just hire an intern and pay them to classify data for 2 months, like just go through and label it. And then you have a supervised learning task. And instead of spending 8 months trying to understand clustering, all you have to do is build a decision tree and you're good to go, or put it through a random forest algorithm or something of that nature. But like I said, unsupervised learning, it's usually things like clustering, so trying to determine patterns and relationships between different groups in your data. But you also have to have a lot of domain knowledge, right? So how many clusters are there that you would expect to see? Or which kind of lens for higher dimensional data sets should you look at for clustering patterns, right? Like it's really simple to see them in 2 dimensions. Like, you have splotchy there and splotchy there and splotchy there. And it's kind of straightforward to see in 3 dimensions if you expand it out. But then when you start adding additional features, what does that mean? So that's a lot of words on a slide. And the algorithms, the acronyms there, I hate acronyms, which means I probably work in the wrong place because Microsoft loves acronyms. But SVM is support vector machine, KNN is k-nearest neighbors, classification and regression trees is CART, lasso is, I always forget, I think it's least absolute shrinkage and selection operator, but like I said, always forget. PCA is principal component analysis, and that's about it. But like I said, lots of word on a slide. Doesn't really make much sense unless you give a tangible example. So here we go. So say your boss comes to you with a data set, our customers.csv, because it's always a CSV. And you work at a bank, and your boss says, here is all the information we have about people who paid us back money on a loan. So that last column is whether or not they defaulted, whether or not they paid us back. We have age, we have whether or not they're employed, whether or not they own a house, their credit rating, their education, and then that final column. But really, if you're my boss, all you care about is that, right? Like, did they pay me back my money or not? And did they do it on time? So it would be really great if you could take this potential new customer who is 35, who has a job, who doesn't own a house, who has bad credit, who did go to college. What is the likelihood that this person will pay you back or will not pay you back? So that's what you want to know. And you could do something like create a decision tree. And a decision tree is one kind of classification algorithm that I was mentioning before. So remember, for supervised learning, for a classification problem, you're trying to predict a category. And here it's yes or no, like did they default or not. And then you also have to have labeled data to train on. And that's true for this case because we have all of this historic data with yeses or nos for all of our people. So we build out a decision tree. It looks something like this. Probably all of you are familiar with this structure. Each one of the nodes has a question. You trace the values that you have in your data set, and you eventually reach a decision node, which is either grant them a loan or don't grant them a loan, one or the other. So if we follow that logic through for this value, right, a person who's in their 30s, who doesn't own a house, but who is employed and did get educated, yes, the answer is that we should probably give them a loan. There's a high likelihood that they will pay us back. So theoretically, that's machine learning. That's a very simple, very, very simple use case for a decision tree algorithm. And like I said, it doesn't really do anything unless I show you code. So this is a repo that you can go to with a lot of code samples, hopefully. And if it's not, you can yell at me, and then we will fix it. But let's see. So let me bounce out of this guy for a second and bounce into Azure Notebooks. So how many of you, let me try it out, build 42? Because I figured every other build value would be taken, and 42 is a great number. So this is, like I said, a repo with lots of data and lots of notebooks to explore. How many of you guys have seen Azure Whoa, there it goes. Yeah. These are all algorithms, by the way. It looks much more impressive on 3 screens, but they're kind of hard to see now. But yeah, so this is, how many of you have seen Azure Notebooks before? Excellent. So for people who haven't, that's your homework for today. Like, just go to notebooks.azure.com and kind of explore all of the tutorials that we have available there. There are a ton. They're for F#, an introduction to R, an introduction to Python, an introduction to machine learning, just lots and lots of different resources for you to use and to explore. But they're all interactive programming environments. And what does that look like? So here, I have a Jupyter notebook running against an R kernel. And you can see that the last time I presented this was at Women Who Code Connect. But you double click, and suddenly the code that's in the cell is exposed if it's markdown, so you can change it. If I wanted to change it here to be build, because that's where we're all at today, Shift-Enter, and it goes. The code in the cells is also dynamic, so you don't have to compile anything. You can just pull it in, run it, and it gives you back responses. So if I wanted to add an additional cell, since this is R, if I'm remembering it correctly, it's installed.packages to see what I've got in my environment. This should spit back a table of every package. Yep, there we go. Every package I've got in R, their versions, their priorities, their locations, their linking to. And as you can see, there are quite a bit added into notebooks.azure.com just out of the bat. So lots of deep learning, machine learning, data analysis packages. Python's kind of the same way. And in order to see kind of the Python packages that you've got installed in a notebook, it would be a very similar process. But yeah, so you can add cells, you can delete them, you can do immediate visualizations, and you can pull in data from a variety of sources. So here I'm pulling in that CSV file that I showed you before, and it's got a lot of different features. And I want you to think of features as columns in an Excel spreadsheet. So they're just columns in an Excel spreadsheet, and then records are just rows. So here we have, it looks like 17 different columns. That last one is the default column, so yes or no. And it's telling us a lot of information about the types, right? So integer, factor, which is categorical variable, and how many different levels that we have associated with each of them. So once we pull in the data, we would get a look at it to kind of understand the distributions, right? So it looks like the majority of people did pay us back, 70% did and 30% did not. If we have 1,000 records in the data set, 1,000 rows. I would go through and I would randomize all the data, which we can do because it's not time series data. And then I would divide it up into subsets for training and for testing purposes. So usually you would have a training, a test, and a validation set, or you would do some sort of cross-validation for your machine learning. This is very simple. Don't do this in real life because you probably won't have that great of performance. But I divided it up into 90% train and 10% tests. And we see that the distribution is very similar, so around 70% and 30%. And then once we divide things into training and test data sets, to create a model, a machine learning model, it is one line of code. And that's all you have to do, right? So you're basically just saying, of your training data set, the one that you want to use to predict on is that last column. So that's the last column. And then you want to base that prediction on everything except the last column. And that's all. So there's a lot of, what's the word for it? There's a lot of kind of stigma and fear, I feel, around machine learning. Like, oh man, that's hard. I need math and science degrees and lots of acronyms and behind my name. And that's not really true. So my background, I did geophysics and applied math, which was fun and not very useful in this software world, I guess. But it was, to be perfectly honest, all of the deep learning and machine learning work that I've done has been leveraging open source packages that other people have created. So in Python, you have this great set of algorithms called scikit-learn, which have been created by lots of folks, kind of peer-reviewed, stress-tested, based on kind of the best academic research that we have to date. And if you want to add an additional algorithm, there's a really lengthy review process. But to implement that algorithm, it's less than 10 lines of code. Same story for R. To implement an algorithm, less than 10 lines of code. TensorFlow looks very obfuscated. Like it's not, there's a lot of boilerplate. It's not very fun to write, and it's not very fun to look at. But Keras and some other kind of developer-facing tooling removes that obfuscation. So it makes it that no matter what algorithm you're implementing, it's probably going to be less than 10 lines of code if you're doing it correctly. And that's awesome, but also a segue. So anyhow, I created a model. Yay, one line of code. Excellent. A decision tree model. And what it gives me back whenever I do a summary of it is a less pretty version of that graphic I just showed you, right? So each one of those little branches would be one of the nodes. And then you would ask a series of questions and divide out the answers. So here you can see all of the branches of our tree and then the final performance that I got. So apparently I got pretty dang good performance, even though I used a lot of data for training, so that's probably a bit overfit. And then this is something called a confusion matrix. So this guy right here. And it tells me how many were true positives and true negatives versus false positives and false negatives. So which ones did I accurately classify and which ones did I not? And then attribute usage, which is basically saying, okay, well, this is the feature that we assume to be most important. And this makes intuitive sense, right? So if I'm concerned with, is somebody paying me back or not, then checking account balance is probably important. If they don't have any money in their bank account, then they probably aren't going to pay me back. So that's how you would create a decision tree. And if you wanted to improve model performance, you could do something called a boosted decision tree, which is, if you're familiar with Monte Carlo, it's just taking a whole bunch of them together. so doing a whole bunch of iterations of a decision tree, and then combining them into one much more powerful model. So it's the mentality that multiple heads are better than one. And with this, you can see the output, and all you have to do in order to run it multiple times is to say trials equals 10 whenever you're doing that one line of code. And when you do that, you get back all of the iterations of the decision tree, and then a final performance reading. So you can see that our boost is 3.4% in terms of the accuracy, and the attribute usage again makes intuitive sense. So checking account balance, the duration of the loan, how much the loan was for, how long they've been employed, and then other features such as whether or not they own a phone and how long they've lived wherever they've lived aren't considered to be as much of importance. So that's cool, and that's traditional machine learning. There are hundreds of algorithms to support typical machine learning tasks. So things that you would expect to see in a textbook from like the 90s. And they're all just as straightforward to use. You bring in some data, you divide it into training and test sets, you do maybe some feature engineering, or you remove null values, and then you just use less than 10 lines of code to implement that algorithm. So that sounds like magic, right? And nothing, no free lunches and stuff. So why would it be problematic? Well, one example, your data usually looks more like that, right? Like it's never clean. It's never in the format that you need it to be. It's all floats when you need integers, or it's all integers when you need floats, or the sampling rate changes, or there aren't consistencies for capitalization, or maybe you have some missing values for whether or not they defaulted, or maybe all of the data source for Pennsylvania is non-existent, and it's just not it's not ever a straightforward task in order to get your data in and to get it into a structured format. It also comes in a variety of sources, right? So you have XML files that you might need to parse, or database tables that you might need to query. CSV files, you might have to parse JSON as well if you have a streaming data source. Lots and lots of different source of truth for data. And then also, what about other features, right? And that's really, really hard to see. So other sources of features could be trust me to say that that's age and that's amount. But other sources of features could be very important. So for example, we found doing our analysis of the full CSV file that whether or not they have money in their bank account is most important, but that wasn't necessarily included in the original CSV that our boss gave us. So you as a data scientist would be tasked with saying like, oh, I think that would be a very, very important feature to include in our analysis. We need to find a source of it, and we need to integrate it with our existing data set. So the point is that traditional machine learning can be extremely effective and requires less hardware than deep learning. So you saw that I was able to run it on a Jupyter Notebook in a browser. You can run it on very, very lightweight hardware. But it requires a lot of additional work up front and behind the scenes. And it's also much better for well-defined specific tasks where your data is alphanumeric. So when you have text and when you have numeric values. So that's machine learning. And now ultra buzzword. So deep learning, which is a subset of machine learning. So artificial intelligence, big overarching thing. Machine learning, subset of artificial intelligence. Deep learning, subset of machine learning. And deep learning is learning underlying features in data by using deep neural networks. So being able to apply specific methodologies to understand very specific problem spaces using deep neural networks. And how is that used, right? And it's a lot of ways. So for example, image recognition. We saw a whole bunch of examples of that yesterday. So automatically being able to detect statues or people or even specific people in different environments. So being able to load a subset of your employee faces and detect every single one of them in video footage around your company, which is very big brothery, but also kind of a use case that you might want to employ. And also being able to detect diseases, right? So here you have an example from a recent TensorFlow paper where you have X-ray images of lungs, and you have them classified literally into two folders, one that says cancer and one that says not cancer. So if you were in Scott's keynote where he had the Scott versus not Scott IoT classifier, same general idea. All you have to do is stick your algorithm on it, and it understands what a tumor would be. And that's very powerful. There was also another recent case with diabetic retinopathy, which is, so diabetic retinopathy is completely treatable. It's something that you can detect by looking at images of eyes. And if you catch it early enough and you treat it early enough, then the person's fine. But if you don't catch it and you don't treat it, then a person goes blind. And that impacts hundreds of thousands of folks around the world every single year. And the only roadblock to getting people diagnosed and treated, because it's not super expensive to treat either, is just having somebody look at the picture of the eye and say, yes, that is diabetic retinopathy, or nope, you're fine, go home. So if you can accelerate kind of the classification of yes, that's diabetic retinopathy versus not, you're able to get a lot of people who would initially go blind treated in time. And that's what was created with TensorFlow. There was actually a device that the FDA recently approved that takes an image of an eye and automatically says, yes, you know, that's something that should be treated. Yes?
Something like that, like there is so it doesn't really hardware requirements of how many images, like, so what's the scale that you're talking about?
Gotcha. So the question was, what are the hardware requirements in order to implement a model like this? And it varies. So for example, right, to do it in production was the question. So how much data would you need to train on in order to implement a deep learning model for production? And it is, like I said, the requirements vary dependent on what you want to do. So something, this is a segue, but it's a good background if you would like to try something like our custom vision AI, because it's the theoretical background of why that works. There's a thing called transfer learning, which is basically taking an existing deep learning model that's already been trained. So Google trained a model on, you know, however many millions of images, or Microsoft trained a model on how many millions of images that we have access to, you know, everything that we've indexed on the internet. And that takes, you know, days, often weeks, on very, 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 very powerful hardware that my boss won't let me play with most of the time. So, so that happens. We train this model. It takes a long time, very expensive. But once the model's been created, it isn't like, you know, the terabytes of data that took to train it. And it isn't, you know, you don't need super duper powerful hardware in order to do inferencing. So the model is actually much, much smaller than the original data sets. And like you can take the model and start building additional neural network solutions on top of it. So the low-level features have been learned, the mid-level features have been learned, some of the higher-level features, and now you just add on some additional layers, and you're good to go. So there was a recent talk that I gave at AnacondaCon about, has anybody ever seen the movie Clueless? Yes? I'm probably dating myself by saying I love it, but it's one of my favorite movies, and mostly because Cher has the main character has this thing on her closet that looks like a computer, and she clicks it and it tells her whenever clothes match or not, and that's awesome because I'm really bad at clothes. And it would be great to me to have like this technology solution that can tell me when I'm making a bad life decision on what to wear. So I built it. Like like whether the like specific types of clothing, so punk versus princessy versus kind of conservative and a couple of other categories. And all it took to train that kind of match does not match classifier is about 100 images. So a good rule of thumb for transfer learning, to train a production quality algorithm for every category that you have, you need at least 100 images. And obviously it gets better based on the more refined the model is to your task. So there's this thing, and again, segue, but this is useful if you want to do I promise it's useful. If you want to do TensorFlow on Azure, there's this thing called the Cafe Model Zoo. Cafe Model Zoo. And I'll put a link on the repo for this guy too. But basically, this is just a markdown file with the man. So other fun fact about Paige, I am not a Windows person. I usually, all of my laptops were running Ubuntu before I came here. And I mean, I used Windows at work, but mostly it was Linux. But yeah, so here is a markdown file with all sorts of models that have been open sourced. So emotion recognition in the wild, like if you wanted to train based on specific emotions, that would probably be useful. There's also one, I think I saw, yeah, deep yeast. Like what is that, you know, like training on yeast. But lots of very specific use cases. And if you get a model that has been trained to very high accuracy for those niche tasks as well, you're probably you'll be able to get by with less data. But right now, in terms of like medical use cases, there are a ton of models that have been open sourced, specifically around, like I said, detecting tumors in X-rays, detecting like anomalies in sort of medical imagery. I think that Microsoft has a use case where we're able to detect leprosy. So yeah, it basically, it depends on your use case and the model that you use as the basis to train. Because I'm telling you, like, there are some companies that have access to, you know, millions and billions of classified images, right? Like images that have been tagged. Like, yes, this is a dog, this is a cat. But most folks don't, right? Like I certainly don't have hard drives hanging out in my apartment of lots and lots of cool images that I can use for my deep learning models. So being able to use one of these guys is incredibly, incredibly important. And there are, like I said, thousands that have been open sourced that you can use as the grounding of your model.
What about inference time?
The inference time, so it depends, again, on what you're using, right? So the question was, what is the inference time for models that have already been created? And so I believe we heard yesterday from hopefully multiple people. I think multiple people were supposed to talk about it, but FPGAs are a thing now. I'm not telling untruths, right? Like that was announced that FPGAs are, okay, cool. So FPGAs are a thing, yay. And that we can talk about, yay. And our inferencing time on FPGAs is actually incredibly, incredibly quick. It's like near real time. And inferencing is just saying like the time it takes to classify a thing. So that's a dog, that's a cat, that's good, that's bad, that's give them a loan, don't give them a loan, that sort of thing. So TPUs are a bit, tensor processing units from Google are a bit slower, but don't want to go down too much of a rabbit hole. So we'll talk about that soon, I promise. So images, that's another use case. Text, this is what it looks like whenever you give a recurrent neural network all of the Harry Potter books. Harry Potter and the portrait of what looked like a large pile of ash, which sounds reasonable, you know, given J.K. Rowling's word choice. But yes, so being able to take text, automatically create things like n-grams, which are just keywords, being able to take a sentence or a paragraph and then rewrite it in the style of another author. So there have been really, really interesting neural network case studies where you have like rap lyrics and you turn them into Shakespeare or vice versa. And it's just because you have the data to train massive text files based on that. And then also kind of more time series-ish data like sound. So being able to create music and I don't promise that it sounds good, but it's music from just using neural networks, or being able to automatically, like, so you write, if any of you are musicians, you just write a basic tune, right, like a little melody, and then it can automatically create additional parts for other instruments that you want to include within that. And then also, of course, speech to text, right? So there was that great demo yesterday with Harry Shum, I believe it was Harry Shum's keynote, where he is speaking in Chinese and his coworker is able to understand even though he is deaf, right? Like, so automatic real-time, being able to speak in a variety of languages and have everyone understand each other. So it's like whenever you upload a video to YouTube, it's automatically closed captioned for you. And it's not because, you know, there's somebody somewhere that's frantically typing. What you're talking about is you're going fishing, or whatever is the context of the video that was uploaded. But it's just because there's a speech-to-text algorithm that's working quite fast and is part of the uploading process. And a whole heck of a lot more. So AlphaGo, that's generative adversarial networks, which are basically two neural networks kind of fighting each other and improving each other until they finally reach whatever goal that you set. You're able to take art, so Starry Night, and transpose it on top of the Mona Lisa. You're able to do automatic detection for vehicles or for people. And like you know, apart and aside from the ethics, like the Uber case study that was, or the Uber incident that happened just recently. So being able to do all of those tasks is incredibly cool, or at least it's really cool to me. So deep learning has become really popular recently. And why is that, right? Like, I think that 5 years ago, we probably wouldn't be having this conversation. And it's for a lot of reasons. So for example, deep learning is now more accurate than humans. It's more accurate at making, it's more accurate at doing translations. So instead of having a translator on site in person, you can have, I think, close to 95 or 93% accuracy, just taking speech to text and doing translation that way. Google used to have translate.google.com. I think it still exists. But the model backing it used to be something like 500,000 lines of code, lots and lots of very explicit rules. So those traditional programming paradigms that I was mentioning before, lots of statistical models. Like, and again, you know, just imagine like 500,000 lines of code, and was also very slow. So they couldn't scale it the way that they wanted to. They were able to replace it with 100 lines of TensorFlow. And it's now much more powerful than it was previously. And then also the same for images, right? Like, so recently, I think 2 years ago, we passed the human threshold for image classification. So being able to recognize specific things in images, computers are now better than humans. Though that's, okay, so that's not necessarily true. There's this guy named Andre Karpathy, who used to work at OpenAI. Now he's the head of data science at Tesla. And when he was a grad student at Stanford, he went through this massive corpus of images, so tens of thousands, hundreds of thousands of images, and hand classified each one. So an image would pop on the screen, he would say, that's a cat, that's a panther, that's a dog, that's a ball, you know, that sort of thing. which maybe tells us a little bit more about how interesting his grad student life was than anything else. But yeah, so he sat in his dorm room and did that 4 months, and then had a set of images that he trained himself on. So like that would pop up, and he would try to classify, and then he guessed or he calculated how correct he was, and he was like 95% correct. So our threshold for like how good are people at recognizing images is 95%, because Andre Karpathy sat in his dorm room and looked at a lot of images. But seriously, that's what the benchmark was. But now neural networks are better at it. So maybe Andre Karpathy is just bad at recognizing images. But regardless, deep learning is pretty good. And then also voice and sound. So if everybody in this room started talking all at once, it would be really difficult for me to pick up somebody in the back. Like a very specific voice, but a neural network would be able to do that quite easily. And then also specialized hardware. So FPGAs, we just mentioned. GPUs have been around for a while, and they're great for very specific portions of the deep learning workflow. So CPUs, great for kind of sequential tasks. And then when you get to kind of the layer aspect of neural networks, you can break it up into easily parallelizable chunks, and that's what GPUs are great for. And then custom ASICs like TPUs, where algorithms have essentially been burned into silicon. So these chips are incredibly performant for TensorFlow, TensorFlow-related work tasks. And then lots of data, but that's obvious, right? And lots of open source libraries for all of us to use without having to roll our own machine learning algorithms. So getting started with artificial intelligence. You can create your own model or build off somebody else's. And creating your own model on Azure, you have a variety of choices. So you can do Azure Databricks, which we saw yesterday. You can do something called Azure Notebooks, and these have a lot of the libraries preloaded. You can use our deep learning virtual machines. Or you can develop locally even. So say you have a GPU-enabled box in your desktop environment, and you want to ping the data that you've got on Azure. You can do that too. I don't recommend it. I do not recommend the last one at all, because you're going to have performance struggle buses. But Azure Databricks, Azure Notebooks, and deep learning virtual machines are all incredibly they're all incredibly great workspaces for building out deep learning networks. So how many of you are currently using Databricks? Whoa. Just a couple. Okay, and Azure Notebooks we already asked about, and what about deep learning virtual machines? How many of you have heard of them? Okay, so let's talk about that for a little bit. So Azure Databricks, and let me bounce to, sorry, there's a delay whenever oh no, spinning wheel of death. So if I bounce to Azure Databricks, you should see something like this. Now I'm remembering like why the mouse I configured in a different way, so it wouldn't do the bounce back. But so Azure Databricks was Databricks was a company that was created by the people who created Apache Spark at Berkeley. So they created this magnificent open source library for doing cluster kind of analysis on cluster computers, clusters, right? Like so distributed processing of data, being able to pull in things in a streaming manner. And then they realized that it was really hard for most people to be able to do that, and they built a company to make it easier, which is smart. And I wish I had done that in grad school. But it was kind of the same idea, the same mentality behind Cloudera, is you have all of these great open source tools that are often very difficult to use and very difficult to integrate with other things. So let's build out a company that kind of manages that chaos for people and makes a very performant solution. So all you have to worry about is writing your code, doing your data science, doing your machine learning, and we'll take care of all of the headaches for you with regard to clusters and those sorts of things. So Databricks, to get started with it on Azure is very simple. All you would do is go to the Azure portal, and then you would provision a data science workspace on Databricks. So let's walk through that today. And you can look at my real dashboard instead of the one that we made for build, which has the reminder telling me that I'm using too much money. Yeah. But yeah, so all you would have to do is go to create a resource, look up Databricks, and it'll show you where it is there. All you would do is create a workspace, and it would take you directly to where the workspace is housed. If I click this, you can see one of the existing workspaces that we were using yesterday. And there are a lot of getting started materials, kind of tutorials, and useful information for you to get started. If you wanted to use Azure Notebooks, you don't even need to have sort of a credit card-based account on Azure. All you would have to do is go to notebooks.azure.com, and all of the TensorFlow libraries have already been created. So if we take a look at the libraries that I've got in my repo currently, if I go to build 2018, if I wanted to take a look at one of our Keras tutorials today, you can see it's automatically launched, and it's a similar environment to what I had before. You double click, you can change the markdown, and you can also pull in any of the TensorFlow associated libraries. The only caveat I want to mention here is that with a Databricks environment, you're capable of using a machine with GPU acceleration. On Azure Notebooks currently, we do not have GPU acceleration. So it's just CPU-based analysis, and that means that it's probably going to be a little bit slower. If you would like to provision your own deep learning workspace, all you would have to do is go to the portal and create a resource. You would go to compute, and then, or actually, let me just look for it. Data Science Virtual Machine for Linux, or for CentOS, which I don't know anybody who uses CentOS, or for Windows. And Windows and Ubuntu, far and away the most popular ones. But they come preloaded with tons and tons of resources. So if you look in the included tools link, you're taken to docs.microsoft.com, and it runs through the entire gambit of, you get R, you get Microsoft Office. If this is a Windows machine, you get Anaconda, which is a very popular Python distribution. You get lots and lots of data science tools and data science packages, RStudio Desktop, Jupyter Notebooks, different kind of drag and drop environments for machine learning, XGBoost, deep learning tools, and lots of others. So all of that, why would we do this, right? Like, what is the mentality behind having a deep learning virtual machine? It's because package management is hard, and because it also takes a ton of time in order to spin up a deep learning or to spin up a virtual machine with all of this tooling added yourself. Like, if you wanted to download all of this, it would probably, it would take hours, if not a full day, in order to get everything downloaded and configured appropriately. Whereas if you just spin up a deep learning VM, suddenly you don't have to worry about driver issues. You don't have to worry about whether your Python path is where it's supposed to be for specific, for other things, or if you have multiple Python paths for 2.7 and 3.5, if you still haven't made the leap to 3. So it's a deep learning virtual machine I highly recommend. You can get started with it for free, but just a CPU-enabled machine. So if you just want to see what all the tooling capable is, and I recommend using X2Go as an interface for it. So that's an interface that allows you to look at your virtual machine exactly the same way as you would a virtual machine that you're running on your local machine. So we covered Databricks, we covered notebooks, and deep learning virtual machines. And those are the best places to run TensorFlow on Azure. What is TensorFlow? So TensorFlow is an open source machine learning framework that was created by Google. And it was used internally for a long time under a whole bunch of names before it went to the public a couple of years ago. Since then, there have been 2 TensorFlow developer summits, and I highly recommend watching all of the talks there. They get pretty technical, and they're quite useful. And then, what is Keras? Keras is a developer-facing front end for those high-level neural networks. So if you've ever used Python, there's this thing called NumPy, which is very similar to TensorFlow. And NumPy is excruciatingly painful to use by itself. So nobody ever just is like, oh man, I can't wait to write me some NumPy. It's like we're gonna import scikit-learn, so import sklearn, and then use all of the algorithms in there that are, they're built how you would want to architect an algorithm to take advantage of all of the great capabilities of NumPy, but you don't have to have the struggle bus of working with it yourself. So Keras is intuitive. It's open source. It was created by this guy named Francois Choulet, who also works at Google. And I highly recommend this book, this Deep Learning with Python book, because it has a ton of friendly interfaces for Keras. And the naming conventions are also very, very, they're very straightforward. And if you have experience with scikit-learn, then they're consistent with that. So user-friendly API. Usually you can complete with 10 lines of Keras what it would take 200 lines of TensorFlow to architect. And to show that as an example, let's take a look at the Hello World example that I have in the repo. Excellent. So I hate the iris data set with a passion, and all of you should hate it too. But what it is, gosh dang, it's like wanting me to play video games or something. I can wait. But yeah, so the iris data set, I hate it with a passion. All of you should hate it too. It is the first and usually only tutorial included with any deep learning system or any machine learning system. So it's you pull in this iris data set that like I said is usually included in whatever framework you're using. People show you how to do a linear model, and then it's like, oh yeah, by the way, you can do more advanced solutions too. Have fun figuring out how. But that's what this is. So I apologize. But it is kind of a good first look at what the differences would be between TensorFlow and between Keras and between scikit-learn. So this is an example of scikit-learn and Keras doing the iris classification task. And we're also going to take a look at, so this is another example that I will share. We're going to take a look at the classification with eager execution for TensorFlow in the collab space. Or we can just look at the one that they have on the website. That works too. Looks like their product isn't working. That's nice. Cool. But you set up the program, you run eager execution, you go through the problem. None of this looks sort of intuitive, right? Like you have underscores, you have dots. I don't understand the os.path.base name. Like, what does that mean? You inspect your data. You parse CSVs. This is also not very consistent with typical Python conventions. You have to train data sets explicitly. You use example features. You add some layers. And it's usually, it's kind of a headache and a half to just create a model with just TensorFlow itself. If you wanted to do it with Keras, the crux is similar to what I was mentioning before. So this is the version with scikit-learn, so just a couple of lines of code. With Keras, it's very similar in that to create the model, you initialize it. So you say that you want to create a sequential model. You add layers and their shapes, and you specify an activation function. And then you define the last layer, which would be sort of a classification layer here since we're using softmax. So softmax, if you ever see that, it means that we're predicting out a category. But that's it. So you pull in your data, 5 lines of code, and you've got a neural network classifier with pretty good accuracy. And I also have some links down there at the bottom if you want to play with it further. But that's about it. So Keras automatically installed on every deep learning virtual machine in Azure, automatically installed in Azure Notebooks, and I believe it's automatically available in Databricks notebooks as well. So you don't have to worry about configuring it or doing anything there. If you wanted to do, so there seems to be a little bit of confusion to me on what a neural network is actually doing when it's making a decision. So like in my previous work, one of the reasons that we always chose to go with more typical machine learning tasks was because the models were very easily inspected. So you would be able to say like, oh, okay, I explicitly know why it made that decision. Like I was able to, so if you have a decision tree model, you can point back to that output that I showed you before, and you could say like, oh, well, this person had a bank account balance of less than this, their age was this, they had been at their residence for less than this amount, so we made this decision. And that way, if somebody comes back and tries to sue you for whatever decision you made, you can point back to the logic that your machine learning model was using to define that decision. And you know, you can at least point to a model making decisions explicitly instead of just you know saying, well, the computer told me to do it, and I just decided to. Deep learning models are very, very different. So they're very difficult to inspect. You can't ever really tell why a deep learning model made the decision that it made. There are some introspection tools like TensorFlow, or TensorBoard rather, included with TensorFlow, that allow you to kind of poke and peek in certain components of your network. But it still doesn't tell you like, oh, I decided this was a cat because it had whiskers, or oh, I decided that this was a dog because the snout was kind of pointy. It's still just very, very obfuscated as to why those decisions are being made. And there's even a class of work now about how, like, what is the minimum amount of, what's the minimum amount of noise that you need to include into a piece of data for your classification model to not classify it correctly. So there's a great paper too that goes into, so if you have a picture of a cat and you've trained it as a cat and your neural network is, you know, 85% sure that it's a cat, you can stick one red pixel in a very specific location on that image, and then suddenly your neural network thinks it's a gun, or a dog, or something else, and that's not exaggerating. Like, it's called a single pixel attack. And also there's another great research paper from this group called Clever Hans that showed that if you had a neural network that classified a picture of a panda, you introduce 0.07% noise, so just random noise to the image. To a human, it still looks exactly like a panda, like exactly the same image. But suddenly your neural network thinks that it's a gibbon, like with just 0.07% random noise. So you can imagine how sensitive that would be, especially for high consequence tasks. Like if you're working in the government and your job is to have satellite images come in, and you're supposed to be looking for bomb locations in these satellite images. And suddenly some nefarious person, either internally or externally, just introduces 0.07% noise to all of your satellite images. They still look the same to you, transparent or kind of superficially. But suddenly, if you had built a classifier on top of those satellite images, it could say, oh, hey, I think that this school is a bomb location, or something of that nature. So being very, very vigilant about data security and being very vigilant about any changes made to existing data sources is incredibly, incredibly important for any neural network task. But the way that they're making their decision and the way that it's so very, very difficult, or the reason that it's so very difficult to be able to introspect it, is because, so I want you to imagine, again, I'm a very visual person, so things don't really make sense if I don't have visuals. If you imagine that you're working at a cheddar cheese factory, and the reason I chose this is because it's not the Iris data set, and there is a cheddar cheese data set that's open sourced. And also I love cheese. But if your boss tasked you with finding out, okay, well, why does a certain cheese taste better than another? Like, we have data about acetic acid, H2S, and lactic acid. And we also have like this very unscientific taste category with, like how good is the taste? But tell me why one cheese tastes better than the other. Well, that's cool. I could try to make some sort of regression, or usually this wouldn't be a linear regression task probably. It would probably be a regression task with kind of interaction effects. So but like I said, just a very, very simplified example. And I would take those three features that would impact taste, and I would take a look at relationships to see like which one could potentially be impacting, right? So it looks here like there might be kind of a linear relationship, but there's an awful lot of spread in the upper right for H2S. And then for lactic acid, that looks like a little bit more of a linear relationship, but there might be a little bit of an exponential curve too. And then the other one, there's just so much spread regardless, right, for acetic acid. So as a human, it's really difficult for me to pick out a direct relationship between this data set, even though it's incredibly, incredibly small. So how would I do it with a neural network? And deep learning is really, really good at dealing with high-dimensional data. So data, think of that as data with lots and lots and lots of feature columns. So before, with our very small-scale example on machine learning, we just had like 17 columns, very, very tiny data set, only 1,000 rows. Deep learning is really great at dealing with massive amounts of data. And then also data with thousands of features in its feature space. We can also use many different layers of nodes with things like forward propagation, back propagation, and this thing called gradient descent. And like I said, many applications in industry. So you would want to architect a neural network solution to meet the need of your particular use case. So convolutional neural nets, they work in some spaces, but if you have time series data, you would probably want to use an RNN. Or if you have text-based data, that would probably be better as well. So there also, you would also have something called hidden layers. So they can get as deep as the thousands. Usually in production deep learning systems, I've seen them to be like 7 to 10 hidden layers. And you would go about and manually tweak the number of nodes per layers and the activation functions used for them. So if you wanted to try it with the data set that we just had, right? So this CSV file that I showed you, if we go back a little bit. So we have 4.543 and some others. If you wanted to create a neural network manually, what you would do is with just 2 of the features, what you would do is you would have the initial values, so 4.543, 3.135. You would have weights for each one of these connectors for the nodes. and then you would apply the weights to get the values for the hidden layers. Then you would have some additional weights that you would use to calculate an output layer. And if you assume all the weights that we have are 1, so just to keep it easy, our actual value is 12.3, so we have a pretty substantial error in our output layer if we just have those weight values. And what it looks like in code for feed-forward propagation is something like this. So you would create a NumPy array with those values. You would define specific weights for each of those nodes, and then you would multiply and add the nodes together. So this is the smallest, tiniest single example of feed-forward propagation that TensorFlow is doing in the background for you in kind of an automated way. And then you would have, the hidden layer calculation part, and you would print out what the actual value would be and what your loss is. So we can do better because, like I said, that was not very straightforward as a classification or a regression task. So we can use linear and nonlinear functions to apply to each one of those nodes and improve our performance. And this is sort of the standard for industry right now is something called a ReLU, which is a rectified linear activation. And what it does is it assumes if the value that you have in a node is negative, you return a 0. If it's positive, you return that value. So that kind of simplifies the problem space a little bit more. Like I said, many functions to choose from. There are 8 examples there, but I recommend if you're starting out, just try it with ReLUs. So the takeaway with deep learning is that all of this handcrafting, this like figuring out of, okay, so imagine as a human being, instead of just of these 2 variables that you have for acetic acid and H2S, you have 1,000. And you have a densely connected layer or a densely connected network where each one of those 1,000 features has to go into however many nodes you have in this next layer, and then all the way through however many layers that you have. You would have to be hand calculating all of those specific relationships, and then also trying to understand what the weights should be between each of those nodes in order to optimize your output. That is a nightmare. It's math. Math is, well, I guess to some people math is kind of a nightmare, but it would be incredibly complicated to do by yourself. So TensorFlow, what it does is no matter how many layers that you have, no matter how many nodes that you've defined, it goes through all of those complex mathematical tasks for you, and through each epoch, it gets better and better at getting correct that last output layer that you're expecting. So instead of you having to figure out all the mathematics behind architecting these solutions, TensorFlow just does it for you. And Keras is kind of the friendly interface that you have to TensorFlow doing all of this magic. And another nice thing about Keras, if you've used Cognitive Toolkit, Keras can also be the front end for that as well. So instead of having to learn just one framework specifically, and frameworks change all the time, right? You have this friendly interface that can connect to multiple ones. So we had error here. So our output layer predicted 15.356, and our actual value was 12.3. And the predictions get hard, right? So this is reduced dimensionality sample. So what we could do is implement something called a loss function. And the lower your loss function, so if you remember yesterday I showed like a longish or a chart with kind of exponential curve drop-offs for loss functions and a number of model iterations cycling through. The loss function is something that you want to minimize. An example of a loss function would be mean squared error. So the concept is something called gradient descent. And what this is think of being on a hill at nighttime, and you need to get to like and you know that there's some sort of valley in front of you. Somewhere around you, there's some sort of valley. So what you would need to do is, as a solution, if you can't see anything, you could feel around you. You could notice the slope. And if the slope was trending downwards, you could assume that probably the valley's in that direction. So you could feel around, say like, oh, that feels kind of deeper, so I'll go over here. And then just repeat that process over and over again, just moving down piecewise until you get to the valley. So that's all gradient descent happens to be. You're just trying to minimize the slope until you get to a place where everything's kind of flat. It's like finding a local minima in calculus, if you remember that. And to calculate the slope for a weight, it would look something like this. So you would calculate the slope of the loss function at the node that you feed into. So that would be 2 times the error. And then you would have a learning rate that you apply to it. And you would go through like this. And then you would also do back propagation to help better understand your system and understand the error and try to minimize it. So remember how I said that TensorFlow goes through all of the headaches of determining weights? It also goes through all of the headaches of determining this stuff too. So you don't have to worry about creating the slopes. You don't have to worry about kind of optimizing based on gradients. And remember, this is done multiple iterative times throughout the runs of the epochs of your neural network. So if you're trying to get any sort of insight into this system, it's going to be incredibly difficult to do. So that's back propagation, and I am apparently out of time because I am incredibly bad at answering questions. I think I should have been, I'm sorry, I should have been quicker about that. But there's, like I said, a repo filled with, there is a repo filled with TensorFlow, Keras, and scikit-learn models at aka.ms/build2018. It also has data and some README files, and also a notebook that shows you how to interact with data that you currently have on Azure. So if you have data in blob storage, if you have data in if you have data in databases or in SQL data warehouses, it shows you how you would go about connecting to all of those on Azure. So that is, and the examples that I give show how you would connect to CSV files both locally and on the cloud as well. So hopefully this has been helpful. I apologize if it hasn't. But yes, and if anybody has any questions, please feel free. Yep. So. Thanks.
Does this work?
Yeah.
A little bit.
Go for it.
So I don't really understand the purpose of Azure Notebooks because it seems like it's there for you to experiment. Okay, it's only for CPUs, but for my tests, I needed to train a learner model, and after 2 hours, it just goes to sleep.
Yeah. So the product roadmap for Azure Notebooks is that eventually they're going to be able to be implemented just internally within a company and also leverage GPUs. So if you wanted to say have an Azure Notebooks that's looking at a GPU that you have in Azure, you can do like some sort of rudimentary analysis and then send a link to one of your teammates. And if they have the same data access permissions and the same machine access permissions, they would be able to look at the analysis that you just created, make modifications, and then save it as well. So it's intended to be kind of a collaborative sharing workspace for these Jupyter notebooks. And
so there will be, like, it's persistent in the way that you pay per hour, or how do you foresee that?
So I'm not part of the product team, but I would imagine that it would probably be implemented as part of a deep learning price thing. So if you that was not a clear sentence. I think if you provisioned a deep learning virtual machine, you would probably have access to this service as part of the capabilities of the deep learning virtual machine.
Okay, and last question. So sorry for being long. So Google has TensorFlow, Facebook has PyTorch and stuff. Microsoft has CNTK, right? But
Microsoft does have CNT.
But what's the future of that? I didn't hear you mentioning it.
Right. So personal opinion. I think that choosing a deep learning framework should be a function of how many quick starts, tutorials, walkthroughs, how well it fits your business need, and also how much code you can copy and paste from Stack Overflow. So, based on that, 95% of deep learning practitioners are using TensorFlow, and TensorFlow runs great on Azure. Like you can do inferencing. You can do TensorFlow inferencing super duper quick with an FPGA. So it's like, I don't care what framework you're using. Like it's on Azure, it all works pretty great. And for Cognitive Toolkit, we'll still continue to use it internally to develop some things with it, specifically around kind of proprietary products, and also it's not like it's technically there. Like the technical capabilities of CNTK are just as good as TensorFlow or PyTorch. It's just that we don't have like this massive thousands of people who are all contributing to the project, and that's what TensorFlow has going for it.
Okay, and you're not aiming to have those developers. That's what I'm
For
hearing.
CNTK, it's like, we'll go to the party that's already there. Like, we don't need to try to throw a party ourselves.
Just one thing related to that.
Mm-hmm.
So yeah, why Azure Notebooks CPU only? I mean, it doesn't seem practical.
But it's going to add GPU capabilities soon. So it should, I think that the last time I saw the product roadmap, that might be something that we're announcing at PyCon, which is Wednesday. So, but the plan definitely is to have GPU capability for Azure Notebooks. So the free version online that anybody can go to will be CPU. But if you have an Azure account and a deep learning VM, you'll be able to use the GPU. Yep.
So you mentioned something about, I think, layering, having a model and layering more attributes on top of it so that you can
Yeah.
reuse it.
Transfer learning.
Right. And I was wondering, is there any, if you could share later on some examples, real-world examples of that?
Absolutely.
The reason I'm asking that question is because you mentioned the 1 pixel attack and so on and so forth. So if a deep learning model is so sensitive, how can you even make it even more complex? Essentially use it as a black box and then put something on top, while the black box is so sensitive. So I would love to learn more about that.
Absolutely, and I can share too. So this one was filmed, and I probably shouldn't. Let's see. Deep fashion. Come on, open up the thing. Open. AnacondaCon. So that was the presentation that I gave at AnacondaCon. So it's online, and you can look at it as well. And I believe all of the code is online as too. But it goes a little bit more into the theory, and then also how you would go about doing data sourcing, and kind of some of the choices that you would need to make for GPU versus FPGA versus ASIC. So I can post a link to that as well.
Perfect. Thank you.
Yep, definitely. Yep.
Something on the same line. I'm probably at a more naive state, but I work with a lot of lexicals, and
A lot of what now?
lexicals.
Lexicals. Okay,
Yes.
cool.
And each of these lexicals translate to a list of descriptions for those lexicals. Now, these descriptions are created based on some rules and some patterns. What I'm trying to do with moving forward is, try to build this model based on the existing data set I have, and create new rules based on some suggested new list of descriptions that comes in from my predicted values. So is that something that we can do with deep learning or on Azure?
You should be able to do it with deep learning, but that sounds like it should be more of a deep dive discussion. So if you email me, I can talk with you a little bit closer about it.
Okay.
But if you can do it with any deep learning framework, you can do it on Azure.
Okay.
So that's kind of the long and the short of it. So I'm paige.bailey@microsoft.com.
All right, thanks,
Yep.
Paige.
Thank you. Yep.
Hi, you mentioned hidden layers and you can choose the number of them. What guides that?
Yeah.
It
so
seems like a magic number.
that is a great question, and it is kind of a magic number. So
Perfect.
unfortunately, so a lot of there hasn't been a lot of rigorous analysis into mathematical groundings for deep learning. Right now, even if you read through Francois Chalet's book, it's just like, oh yeah, like you'll want to add a couple of layers, and then you'll add some nodes, and then you'll see how the performance increases if you add more nodes, and then you might want to add another layer, and then you might want to change something, and it's just kind of like sort of making these bespoke neural networks, and you can brute force it a lot with hyperparameter tuning. And you do learn a whole bunch of rules of thumb as you kind of build them out yourself, and you understand your data, and you understand what problem task you're trying to solve. But for the most part, it is just kind of like, oh, okay, well, I think this should be a densely connected layer. I think that it should probably need about this many nodes because I have this many features. And it's just kind of, yeah. I wish that there was a good resource that I could point you towards for just rules of thumb, but it doesn't exist. Like, but that's also another huge reason why everybody in this space is so like everybody reads papers all the time. Like there's even so my homepage, whenever I launch Edge, it goes to this thing called Archive Sanity Preserver, which was created by that guy Andre Karpathy, who sat looking at images and hand classifying them, right? And what it does is it cycles through all of the papers on Archive and just spits out all of the most recent deep learning papers. Because if you want to understand like methodologies for specific architectures or performances for specific tasks, you have to read the research. And it also, the other thing is that it changes all the time. So it's not like and that makes it sound more dismal than it is. Like if you try certain the more you build, the better you learn how to architect certain neural networks. And there are best practices, sort of architectural best practices for the types of neural networks that you can implement.
All right, thank you.
Yep.
You'd mentioned shying away from doing the local stuff. Is it just because of package management and configuration, and you got to be like a total nerd in order to get all that stuff taken care of?
So that is a great point. For local data science work, you would need to have small data sets, and you would also like I guess more to what I was pointing to. If you wanted to do local development, but your data's on the cloud, don't do that.
Okay.
Like do, because whatever you're doing locally, like whatever tools that you love and that you use, you can use on a virtual machine in the cloud, and you won't have the crazy latency that you would have if you were trying to do data. And, like if your data is stored in a SQL database here, or it's so massive that no, just do everything in a workbook on the cloud.
Gotcha. Okay.
But if you have a defined problem, a small data set, a high-end machine, and you don't want to do things in the cloud, then that's all the more power to you.
Okay.
Yep.
Cool. Thanks.
Yep.
If you talked about, I guess, building models on top of models. So let's say you wanted, what I'm looking to do is, so if you, I'll use the example. So you have a bicycle race and you have multiple people or a single person crossing the finish line, and they have standard numbers on their backs because they're pinned on, kind of like runners. So would you first maybe create a model that would identify the area, because that white on black or whatever, would you first create a model that would identify sort of an individual rider with that they have a number, and then create another model that would break that? Or would you just classify the numbers that are in like a frame?
Right.
Do you understand what I'm trying to say? So you might have one picture where it has one rider, and it would just be their bib number, and then you might have another picture that would have two bib numbers on it, or three. So would it be better to try to find the individual rider with just that number square and then the numbers, or would you try to do all together?
So the good news is that that's a well-defined task that you don't even need a deep neural network for. So it's, and usually, and you wouldn't want to train on like rider with the badge on the back even. Like you could just train on the number itself. And this has been done for license plates,
Right.
for runners.
Yeah. And also
and
house
such.
numbers, things like that.
Absolutely. So it's kind of you don't have to train for multiple instances of that in a single photo. Like once it learns how to recognize numbers, it recognizes numbers.
But you might have riders stacked on top of each other, right? So my concern is that, you know, the models that are trained would see like 1, 1,
Right.
2, 3, 4, and as opposed to seeing 1, 2, 3, 4, and then 4, 5.
Gotcha.
So that makes, you understand what I'm trying to say? So, because my end goal is to have, you know, the numbers broken out.
Gotcha. So an example would kind of, so this is kind of a more visual example that shows what a neural network would see when it's making a decision, right? Like
Right.
it's not, it would be detecting the bib number configuration. So
Right,
it would
okay.
probably, unless, if you've trained it well, it would probably be
I
able
haven't done very well with my dog, so.
so, but yeah, so that's kind of, and it's much easier than how it sounds. Like it's the training prospect. It takes a lot of trial and error, and a lot of the time it takes data curation. So being very controlling and sort of understanding your data very well. And having a lot of it. But if you've got your data in a good state, you can probably train a neural network to do pretty much anything that you would want for a very well-defined classification task.
Okay, thank you.
Thank you.
Me again.
Yep.
Maybe answering that question, because we do a very similar thing. There are two algorithms, YOLO and single shot object detection. That's exactly what you would need to use here. You just train
Yeah.
on every instance of your data, and it will detect on your images. Pretty cool stuff. My question is, if you have you train your data, how do you proceed to deploy it into production on Azure? You train it like you describe it here, then you have a protobuf or something on TensorFlow.
A
You
dot
wanna-
PB.
Yeah, and you know you want to do inference on scale.
Yeah.
How?
Yeah, so that's a great question. Like once you've built a model, how would you go about productionalizing it? How would you kind of deploy it off into the world? And I do that also in the deep transfer learning talk at AnacondaCon. But so for example, a protobuf file, you could implement it in a container with Flask, and so your developers could ping it as a REST API. And there's a great tutorial on that using Keras on the Keras website. I think it's the most recent blog post that they've had. So you would have your .pb file. You would have a JSON file to specify inputs and outputs, and you would have a file to initialize and run it. You would put that all up into a container, and then you would deploy it with Flask, so it's like a REST API.
So that's TensorFlow serving, or?
So TensorFlow serving is a different option.
Okay.
But TensorFlow serving, I think they only support gRPC right now.
Yeah.
But they do have it on their roadmap to support REST API soon. And I would be thinking, like, I'm kind of hoping that, like, because I don't really get to look at I/O very much today, but tonight I/O will happen, and I'm hoping that that's one of the announcements, is that TensorFlow has like super nice REST API stuff now. But that would be an option, right? So you have a container, you deploy it as kind of a REST API that your application developers can hit, and then that containerized model can also be run on like an IoT edge device if it's small enough, or it can be run, you know, on a Spark cluster, or it can be run locally on your laptop.
Right, but on Azure, that would be data scientist virtual machine, or where do I run that Flask application? Because
So there's something that we have called Azure Model Management, which basically instantiates a serverless way for you to call a machine learning model, right? So you have the container ready and waiting. Somebody pings your thing, and then it sends back, whatever classification response
okay,
you
it's
need.
an alpha function, like a serverless alpha function.
So serverless function is basically. Are you familiar with lambdas on AWS?
Yeah, but that's a lambda, right?
Yeah.
Oh, okay.
Yeah.
Okay, thank you.
You're welcome. Cool. I hope it was useful. Oh, thank you.